In this video, we will do a U-substitution example involving trig functions. So I want to evaluate the antiderivative of tangent of x. Okay, so to get this started, let's rewrite tangent as sine over cosine. And this is nice because I see a function and its derivative in here, and that's really great for U-substitution. So I'm going to let u be equal to cosine x. And if I do that, du would be negative sine x dx. So let's isolate the dx. So that'll give us du over negative sine x equals dx. So now if we plug in, we get the integral of sine x over the denominator's u, and then dx is du over negative sine x. Okay, so the signs cancel and we'll end up with a negative integral of 1 over u du. And this antiderivative, we know this is going to be negative ln absolute value of u plus c. Okay, and then I have to plug back in for what u was. So I'll get negative ln absolute value of cosine x plus c. And that's my antiderivative of tangent x. So in a textbook, typically they would have this written in a slightly different form, and I want to show you how we can get it to that slightly more simplified form. Okay, so what I'm going to do is simplify this. So to simplify this, I'm going to notice that that negative in front of the ln, I can think of this as a negative 1. And when I have a coefficient in front of the ln, I can bring it inside as the power. So that'll give me ln, and I can even bring it inside the absolute value, cosine of x being raised to the negative 1 power, and then plus c. And then cosine to the negative 1 power, well, that's 1 over cosine. But 1 over cosine is secant. So we get ln of secant of x in absolute value, and then plus c, and that's my antiderivative of tangent. So the question I want to ask now is, what if we let u be equal to sine x rather than the cosine x? So in that case, if I write du, my derivative would be cosine x dx. And seeing this, like I do see a cosine x in my integral, and I do see the dx. And we might think, oh, isn't that a good thing? Isn't it a good thing if I see my du function in the integral? But it's not quite what we want. So we do want, let me put a bubble around this. We do want to see du in our integral, maybe up to a constant multiple, but I don't quite see that because our integral actually has 1 over cosine x dx rather than just cosine x dx. Okay, so that often indicates that maybe using this u-sub isn't the best thing to do, but let's just try it and see what happens. Let's try it anyways. Let's try it anyway. So here was our function. Here was our integral. So if I plug in, the numerator becomes u. I'll still have the cosine on the bottom. And for the dx, well, I have to isolate dx here. I'll get du over cosine x equals dx. So if we plug that in, we'll get du over cosine x getting plugged in. All right, so this becomes the integral of u over cosine squared x du. Okay, so we've done this u-substitution, but it didn't completely get rid of all of the x's. So one thing that we could try is if we have lingering x's, or whatever our old variable is, we could use our u-substitution again. Let's try using u equals sine x again. Okay, I'll put a little bubble around this. Well, right now in my integral, I don't see sine x. I see cosine squared. Okay, but there's a connection between cosine squared and sine squared. So this becomes u over, and cosine squared is 1 minus sine squared. Okay, so I'm using a trig identity there. And then we have the du. So I just use the identity cosine squared x plus sine squared x equals 1. if we just isolate the cosine squared, it becomes 1 minus sine squared x. Okay, so now we have sine in here, so now I can plug in my substitution again. So we get u over 1 minus, and this becomes u squared. Okay, so we're taking this u substitution, and we just plugged it in again. We plugged it in for this sine in here. All right, so now I need to do the integral of u over 1 minus u squared. Well, this is great for another u sub. Okay, and if I need to do another u sub, I should pick a different variable because I already have u in this. So maybe I'll call it t. I'm going to let t be my denominator, 1 minus u squared. And I know this is going to be good because I see the derivative of that in my integral, just off by a constant multiple in the numerator. dt, this derivative, is going to be negative 2u du. And I see that in the numerator, just off by this negative 2 factor. Okay, so if we isolate the du term, we get dt over negative 2u equals du. And now let's plug in. So we'll get this equals u on the top. The bottom is t, and then du is dt over negative 2u. Okay, so this is nice because the u's cancel, and I'll get negative 1/2 integral of 1 over t dt. Okay, this one we know how to do. This is a negative 1/2 ln absolute value of t plus c. Okay, now I got to plug in for the t. So we'll get negative 1/2 ln absolute value of 1 minus u squared plus c. Now I got to plug in for the u because we let u be equal to sine x. Okay, so we got to plug back in. We have to plug it back in twice. And that makes sense because we did 2 u subs. Oh, I guess we did a u sub and then a t sub. So we get 1 minus sine squared x. All right, so now if we use our trig identity, this is negative 1/2 ln absolute value of cosine squared x. So just like when we did the antiderivative the first way, I'm going to simplify this, and I'm going to bring this coefficient, that negative 1/2, inside as the power. So I'll get ln absolute value of cosine squared x. That whole thing to the negative 1/2 power, absolute value, plus c. So if we simplify this thing, so we have cosine squared x is just cosine x being squared. So we have that whole thing to the negative 1/2 power. And when we have a power to a power like this, we multiply the powers. So this is cosine of x, that whole thing to the negative 1 power, which is 1 over cosine x. And that's secant x. So this whole thing is just ln absolute value of secant x, and then plus c. And that's our answer. So we got this same answer using this other u substitution that we had gotten the first way, letting u be equal to cosine x. It's just letting u equal cosine x was a lot better. It was a lot quicker. So what made this first u substitution work better was that du was negative sine x dx. And we saw that in our integral, just off by a constant multiple. Because I see sine x in the right spot, it's in the numerator, just like it is in du. And I see the dx here. This is just off by a constant multiple, that negative 1 factor. And that's what made this u substitution work nicely.